All right, welcome to episode 4 of the Hardware VGA series. So in this series, I'm creating an 80 by 30 VGA text display using 7.4 ACT logic, dual port static RAM, and GAL devices. In this episode, I will present a brief overview of the pixel generator module. That's the module that takes the character and attribute data fetched from video memory and renders them as a sequence of colored pixels on the display. I'll show you a simulation that I use to gain confidence that the design is correct. I will show you what I went through in building the prototype and troubleshooting it, which was fairly interesting, but I did get it working. I'll show you some preliminary software routines and a demo of the display, which shows a little bit of an idea of what it's going to look like when it is eventually rolled out as part of the finished project. I will go through some lessons that I learned in this project, and then I'll talk about what the next steps are. Okay, let's get started. Before we go over the pixel generator hardware design, let's discuss how it works. You may recall from episode 3 that the readout module uses an 8-cycle cadence to time the generation of data addresses to fetch from video memory. At times 1 and 5, the readout module increments the readout address register, outputting the address of a byte to fetch from video memory. At time 1, the generated address is for a character byte, and at time 5, the generated address is for an attribute byte. At time 4, the character byte fetched from VRAM is clocked into the character register. The character data, along with the low 4 bits of the vertical count and 4 bits selecting a font, is used to generate the address of a byte from the font ROM. This byte contains a pattern of 8 pixels which correspond to one row of one displayed character. At time 0, two important events occur. The pixel pattern fetched from the font ROM is clocked into a shift register, and the attribute byte fetched from video memory is clocked into a register. This gives the pixel generator the data it needs to generate a block of 8 pixels to send to the output module. The font ROM stores the pixel pattern so that the most significant bit of each pattern byte, bit 7, is the first pixel that should be sent to the display, with 1 meaning a foreground color pixel and 0 meaning a background color pixel. More generally, the shift register's bit 7 output is the pixel generator's pixel output, and the bit output as bit 7 is the pixel that is sent to the output module. At times 1 through 7, the data in the shift register is shifted 1 bit to the left, meaning that bit 6 becomes bit 7, bit 5 becomes bit 6, and so forth. By shifting the pixel data 7 times after the pattern byte is loaded, all 8 bits of the pattern are sent to the output module. When the counter returns to time 0, another pattern byte and attribute byte will be clocked into the shift register and attribute register, and the process continues. Now that we know the theory of operation, we can understand the pixel generator module schematic. The shift register is implemented as a GAL22V10 device. I originally was planning to use a 7.4 ACT166 shift register. However, this part does not seem to be common, and I was not able to find any for sale. This illustrates an important use case for GAL devices. Not only can they implement arbitrary programmed logic, they also can take the place of standard logic chips that either aren't available or don't operate at the required speed. The GAL22V10 datasheet even mentions this use case. The character register and attribute register are implemented using 7.4 ACT574 parts. The font ROM is an SST27SF512 flash memory chip. I chose this chip because I have quite a few of them. They can be programmed by my T48 programmer, and they have a 70 nanosecond access time, which is sufficiently fast for the pattern data to be ready at the time it needs to be clocked into the shift register. The control signals for the shift register, character register, and attribute register are generated by another GAL22V10. This control GAL uses the same timing signals as the control GAL of the readout module, and its state machine is very similar. I won't discuss the GAL equations, but as always, the complete design is available at the GitHub link in the video description if you're interested. Now that we've covered the pixel generator's theory of operation and schematic, let's take a brief look at the simulation I used to gain confidence that the design would work. Alright, so here's our simulation in Logisim Evolution, and we've seen this simulation before. So what's different now is I have a model of the pixel generator module, and the VRAM is modeled as an 8K ROM device. Alright, let's take a look at the pixel generator. Okay, so here's the pixel generator, and obviously the goal here is to make the simulation the same as the schematic, which, as far as I know, I have done. So a couple things to note here. Logisim Evolution does not actually have a built-in model for the 74574 register, so I just modeled one in Logisim Evolution. It's just 8 D-type flip-flops, so no big deal there. The really important thing about the simulation was actually modeling the behavior of the GAL devices, so that's the shift register and the control GAL. So I won't go into the actual details of these particular aspects of the simulation, but the important thing is that these really are, in principle, equivalent to the behavior of the GAL devices, so therefore, if they work in the simulation, they should work in the prototype. And then the last thing to mention here is the font is modeled as a 4K ROM. In the actual design, it's a 64K ROM. I just didn't model in the simulation the behavior of having multiple fonts, but that's not really crucial to the operation of the simulation. All right, so the most important question here is how do we actually use the simulation to get some confidence that the design is going to work correctly in terms of generating a display? And that's a little bit tricky, but what I did is I'm just visualizing the attribute register, so the background and foreground colors, and also visualizing the contents of the output shift register. And when the simulation runs, I should see those values changing as data is sent to the output module. So the interesting question in terms of using the simulation is how do we know that the values that we're seeing in the attribute register and the shift register do actually indicate correct behavior? And that's a little bit of a tricky question, but what I did is I thought about what pixels are we expecting to see in the first row of the display, the very top row of the display. And so the interesting characteristic of the font that we're using is that most of the characters actually just don't have any pixels set in the first row, so mostly we should just be seeing zeros in the shift register. However, there's one character that does have a pixel set in the top row, which is this caret symbol. So that is ASCII code 94, hex value 9E. So if we look at our test data in the VRAM here, if I scroll down a bit, so in this row that starts hex 84 as the address, there is a caret symbol right here, and that is the first foreground pixel that we should see being output by the pixel generator. All right, so let's try to run the simulation now. So let me generate a reset pulse and then take the system out of reset. All right, so what I'm going to do is I'm going to run it until it starts fetching data from video memory and then try to pause it at the point where it's about to fetch the byte corresponding to that caret character so that we can manually clock the shift register and see that pixel coming out of the shift register. All right, so let's give this a shot. I'm going to start with a fairly high auto tick frequency. 1 kilohertz sounds good. I'll speed this up if I need to. All right, so yeah, we're actually quite close here. So let me slow down the simulation quite a bit. All right, we're very close now, so I'm going to manually clock this. All right, so there is the caret symbol being fetched from video memory. So it's going to take a few cycles until that data is loaded into the shift register. Right, so now we're fetching the attribute. There we go. There's that caret pixel. So we have the 7654 bit 4 is set in that character. So again, if we look at the font editor, there's that pixel. And at this point, I am going to say that I was pretty confident that we had a reasonable design here, that it was going to work correctly in the actual prototype. So at any rate, that's the simulation. Let's go ahead and look at the prototype hardware. All right, so here's my prototype of the pixel generator. So attribute register, character register, font ROM, shift register, control GAL. Once again, just point-to-point soldering on a proto board, and this really cool wire that I got from AliExpress made the job fairly straightforward. All right, so what we will look at next is the actual full setup of the display controller, and I will replicate the experience that I had when I powered it up for the first time with the pixel generator installed. So, word of warning, you are about to see some glitchy video that is fairly ugly and flashy. So if that is something that you don't want to see, then I will put right here the time you should seek to skip over that. Alright, so here's everything set up. This is the 8-bit system. This is the display controller prototype. Here is the pixel generator. What we are seeing up here is the eYoYo LCD display that is showing us our VGA output. Alright, so when I power this up, what we are expecting to see is just the characters and attributes that are in uninitialized video memory, meaning we should see fairly random characters with random attributes. So let me go ahead and power up. Alright, so basically what we can see here is that this is almost kind of right, but as you can see, there are some glitches that happen occasionally and produce incorrect output. So what I believe is happening is that the row begin address register on the readout module, it needs to get clock pulse signals that go high for one cycle to tell it when to load data into the 74ACT273 devices that store the row begin address. And I think what is happening is that there are glitches on that line that provides those clock pulses that causes the row begin address register to load data at the wrong times. And that's basically the reason for these artifacts that we're seeing. So you may recall in the last video, and I'll show a picture of it here, there was a scope trace that showed a glitch on that exact signal that rose above the TTL input high voltage threshold, and so I think that's basically what we're seeing. So what do we do about this? So here is my sort of very ad hoc analysis. I think the problem is that this readout module, it has some long wires, it has no ground plane, it's kind of a worst case scenario for signal integrity. So I think what we potentially need to use is parts that aren't as prone to creating these voltage spikes. And the thing that I tried first was to use 74ALS 163 counters on this board. And my hope was, cross fingers, that will eliminate the ground bounce issues that I think are causing these glitches. Alright, so what I'm going to do is I'm going to replace the 74ACT163 counters on the readout module with 74ALS163 chips, and then we'll power up again and see if things improve. Alright, I've got the 74ALS163 chips installed here in the readout module, so let's power up again. And there we go. That is absolutely rock solid, stable 640 by 480 VGA, showing perfectly reasonable font shapes and attribute colors. So I'm gonna say I was super excited when I reached the point where I had a stable display. I was certainly a little worried that I wasn't going to get to the point where I was able to eliminate the glitches, and it was very gratifying that it turned out to be as easy as using 74ALS logic rather than 74ACT logic. Now I'll give you a brief overview of the software routines I implemented to allow the host system to drive the display controller. I won't describe the implementation of each routine in detail, but I will try to give you a sense of what each routine does. The init function, which is called automatically by the monitor's reset handler, initializes some variables, clears the screen, and installs a handler for the timer interrupt, which is used to blink the cursor. The clear screen function clears the screen by filling the first 3 VRAM banks with default character and attribute values. The fill bank function does the work of filling 1 VRAM bank. The compute adder function translates a text row and column number to the address in VRAM of the character attribute pair corresponding to that row and column. Note that the address is not directly usable by the host system because the VRAM is not directly mapped into the host address space. The map bank function translates a VRAM address to a host address in the 2 kilobyte VRAM access window and selects the correct VRAM bank. When mapbank returns, the caller can directly access the VRAM memory location, for example, to modify the character and attribute at that location. The setBank, setFont, and setAdder functions allow the caller to set the current VRAM bank, the current font, and the current attribute, respectively. The copy_dumb function copies bytes from the host address space into VRAM, selecting the appropriate VRAM bank and translating the destination VRAM address to a host address in the VRAM window. The routine is dumb because it doesn't handle the case that the transfer might cross a bank boundary. The write_dumb function is like copy_dumb, except that rather than copying bytes containing both characters and attributes, it only copies text characters and uses the current attribute as the attribute for each copied character. Together, copy_dumb and write_dumb serve as a very primitive mechanism to allow programs to put data into video memory so it can be displayed on the screen. I think they will likely serve as building blocks for more sophisticated routines. The moveCursor function changes the current cursor position. This task is complicated slightly because the IRQHandler function, which handles the timer interrupt, also accesses the current cursor position, so moveCursor must disable interrupts in order to avoid a data race with IRQHandler. These software routines are fairly rudimentary, but I think they are a useful starting point for more complete software support for the display, and they are sufficient for simple test programs. Alright, so now that I've talked about the software routines, let's finish up by seeing the results of a little test program that I wrote. So let me load the program into the host RAM. So download command, send file, the hardware VGA test program. Alright, so go to address 1000 hex and then S to call the subroutine. And so this is what we see on the display, and this is what I envision that the boot up screen will look like when this is a quote-unquote complete microcomputer system. So a little bit of a banner, a little bit of colors, prompt, cursor. So I guess my thoughts here are this is exactly the kind of display that I wanted, and I'm really excited that this is actually working. I can't even really tell you how exciting this is, given how long it's taken to get to this point. And one thing I do want to mention briefly, so this monitor I bought at a thrift store for $1. So this is a really good illustration of why I think VGA is the sweet spot for displays for these hobby computer systems. Is they're really cheap and yet they look fantastic, and so really pleased with how this turned out. All right, so there's one more demo program I want to run because I did tease it in the intro. So here's a picture of Ingo rendered as text characters, and I think it is fitting because he did help me with this project. Alright, so the display controller works and I'm really pleased. So let me tell you a few things I learned in the process of working on this project. Alright, so the first lesson is simulation is super useful for complex digital designs, and the simulation that I built in Logisim Evolution gave me pretty high confidence that my hardware should work, and I don't think this project actually would have happened without the simulation and the confidence I gained in the simulation. So when I move to FPGAs in the future, this is definitely going to be a major part of the workflow. The second lesson is, I think when you're tackling something that you haven't done before, it is a good idea to simplify as much as possible, to pare down your requirements to the absolute minimum in order to maximize the chances that the project is going to succeed. So a few things that I did in this project are using dual port RAM rather than trying to timeshare the system RAM, which would have been more complicated, using 640 by 480 mode rather than any of the super VGA modes like 800 by 600. I simplified the color model, and I didn't have any provision for a color palette in this design, and all of these simplifications made the project more straightforward and I think contributed to the ultimate success. So the third lesson is about how to construct a prototype, and this was the first project I've worked on where the prototyping was done on protoboards using point-to-point soldering rather than using solderless breadboards, and that was quite nice because I didn't have any anxiety about jumper wires coming loose on a solderless breadboard, which is definitely something that's bitten me in the past. So as you saw in this video, signal integrity can definitely be a challenge when you have lots of flying wires on a protoboard, and in the future I might experiment with more appropriate techniques for high-speed designs such as Manhattan-style construction. All right, so what is going to happen next is I am going to make a PCB of this design, or at least I'm going to try to, and that will come out as part of the DIY 8-bit computer series, so we're kind of done with this specific series about hardware VGA. I am going to continue to work on the software routines, and given that we now have basically all of the major hardware components of this 8-bit computer system in a working form, it might be time to start writing some actual programs for this computer system. And I would also like to return to FPGAs and do a version of this display controller in an FPGA. Given that I know that I have a design that works, I think the time might be right to do that. All right, so see you in the next video.